Hi students, welcome to TIME. In this session, we will discuss about kinematics. Under kinematics, we discuss about types of motion, scalar and vector quantities. Okay. Now, when we talk about physics, physics is a subject which will deal with bulk matter and the phenomena related to that matter. Okay. Now, under physics, we do have so many branches. For example, one branch, such branch is mechanics. Mechanics deals with the bodies and their interaction. How do they interact between themselves and with their surroundings? So, and again, we have one more branch, let's say thermodynamics. Thermodynamics deals with the temperature, heat and their related phenomena. Okay. Similarly, we have some other branch like electromagnetism. Electromagnetism is something which is related to electricity as well as magnetism and their interrelationship and the applications related to those effects. Similarly, we do have light, that the branch of science which we are the physics which will deal with light and its behavior and its relationship with other physical quantities, that's called optics. Like this, we do have a number of branches of physics, out of which when we talk about mechanics, as I told you, mechanics deals with the bodies and their interaction. When I say mechanics is dealing with the bodies and their interaction, then we have different branches under mechanics which will deal with the bodies which are at rest or in motion. Okay. So, the branch of mechanics which will deal with the bodies at rest is called statics, whereas the branch of mechanics which will deal with the bodies of which are in motion, that is called, again there are two branches, one is called kinematics, other is called dynamics. If at all I have these two types of branches this way which are dealing with the motion of the bodies, okay, then there should be some difference between the two, right? So, when I am talking about the motion of the bodies they cannot move on their own. There will be some external force that we know, everybody knew it, right? They don't move on their own, right? So, when we talk about the cause of motion and then talk about the motion, that means when we talk about the motion of the bodies with respect to their cause, then it comes under dynamics. Whereas, when we talk about the motion of the bodies without reference to the cause of motion, then it comes under kinematics. So, basically, it is this particular branch what we are dealing with now, the kinematics. Okay. Let us discuss some definitions in the kinds of motion or the basic definitions involved in kinematics. So, going with the term kinematics. Okay. Kinematics is the study of the motion of the particles or bodies without taking into the account the forces involved. We know that whenever we need to have a motion in a body, there need to be a cause, that is a force. To better understand this, we will take an example. Let us take a smooth surface over here on which I am placing a body of mass m. Okay. It can be either at rest or in motion. I can take it any way. Let us assume that the body is moving from the position A with certain velocity u, and as soon as a force is applied on it, then the velocity is changing. Okay. When the velocity is changing on the application of the force to the new value v at the position B over here, okay, now the total distance travel will be s. That is what I am denoting, and the time it takes for it is t. Now, here we are emphasizing on the velocity initially and velocity at a later stage, that is u, the distance it travels and the time it takes. Relating all these particular physical quantities, we do have some expressions, okay, when what we study under kinematics, that is v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to v square minus u square is equal to 2as. Okay. So, now if you study these particular, if you just observe these particular expressions over here or equations, we do not find any term related to either the force are the mass. That's what the definition of kinematics talk about. We are not talking about the study of the motion of the particles without taking the forces. We are not talking about the force or the mass. Let us now move on to further few more definitions. Okay. Now, when you talk about a particle, we use the word particle, object, bodies like this. When do you say a particle? When I say a particle, particle does mean that without object, any extent, an object without an extent. That means size is very small. Okay. So when the size is considerable, we'll say it is a body or an object, right? And then we talk about rest. When do you say a body is at rest? So we talk about the rest when a particle or a body, its position is not changing with respect to the surroundings. Okay, this is how we define it. A particle is said to be at rest if its position related to the surroundings does not change with respect to time. Whatever the time it goes on, as the time rolls on, if the position of the body is not changing with respect to the surroundings, then only we say that a particle or a body is at rest. As an example, let us say this boy over here is sitting on the floor. So when he is sitting on the floor very comfortably, he is appearing very composed, right? So he is at rest with respect to the surroundings. He is sitting on the floor at rest with respect to surroundings because its position is the same. It is not changing with the surroundings, right? This is how we define rest. We'll move on to one more example. See here, there are two children sitting in the bus. Okay, they are at rest with respect to each other because when I compare their positions, they do not change with time. Okay, that's what the body or particle is said to be at rest, where its position related to the surroundings does not change with time. So the position of this boy and this girl does not change with respect to their surroundings. That means with respect to each other. So they can be considered to be at rest with respect to each other. Okay. Now let us move on to the next definition called motion. Now we saw what is at rest. That means the body's position should not change with respect to the surroundings. If going with that way, then how can you define motion? Do you have any clue? Small guess. Yes, what you said is right. Now the particle is said to be in motion if its position related to the surroundings changes with respect to time. So this is how we define motion. Okay, let us take an example. So when you say the same boy over here, he is appearing to be in motion because he is moving with respect to the surroundings. So he is moving on a push scooter, so he is moving with respect to the surroundings. So he is said to be in motion now. With regards to motion, we do have certain important terms. Okay, important note. What is that? We'll see here. First one is the motion and rest refer to the state of the body described with respect to the surroundings, in relation to the surroundings. When we consider this way, we have one more important note that, okay, if the body is at rest with respect to one particular person, the same body need not be in rest with respect to the other particular person. Okay, that brings us to the another important note where I say a body which is in motion or at rest with respect to one observer need not be in motion with respect to the another observer. Let us take a few examples with respect to this particular note. As I shown you previously, a boy and the girl sitting in the bus, they are at rest with respect to each other. But when the bus starts, they both are in motion with respect to the surroundings. So that is what I mean to say, in motion with respect to one observer need not be in motion with respect to the another observer. If I am talking about that boy and the girl, okay, they both are at rest with respect to each other, but both of them will be in motion with respect to the person who is outside the bus while the bus is in motion. Hope the definitions of these things are clear to you. Students, let us now discuss about the types of motion. So, when I say motion can be classified into so many types. Okay. So, let us see these particular types of motion. One is translational motion, rotational motion, oscillatory or vibratory motion, and random motion. Basically, these are the broad classification into which a motion can be classified into. Again, when you go with translational motion, we do have two types over here, that is rectilinear and again curvilinear. Let us now discuss each and everything in detail. Okay. First, let us go with rectilinear motion in translational motion. When I say rectilinear motion, the rectilinear motion refers to a body moving along a straight path. Okay. So, whenever a body is moving along a straight path, we call it as rectilinear motion. Okay. Let us take an example. So, motion of a vehicle on a straight road. You can see in this picture over here, the path is very straight and long road. So, vehicles are going, if they are going along this particular path without deviation, then we can call it as motion of a vehicle on a straight road. That comes under rectilinear motion. Okay. That is under translation motion. Basically, when I say translatory motion, the body moves from one position to the other position. Okay. That is what you call it as translatory motion, and this is rectilinear motion. Another type of translational motion is what? Curvilinear motion. When I talk about curvilinear motion, just guess it is different from rectilinear motion. That means it is not a straight path. Yes, you are right. So, it is like a curved path. Whenever a body is going along a curved path, this will come under curvilinear motion, under translatory motion. Okay. As an example, we will consider, see, motion of a vehicle on a curved road. You can see in this picture over here, the car appears to be going straight, but there is a curve ahead. Okay. So, it needs to take a left turn over there. Whereas, in this picture over here, you can see the signboards over there. There is a signboard towards taking a direction towards the right side. So, it is not a straight road, it is a curved road. Okay. Such type of signboards you will be able to observe on the service roads, where these service roads will merge into a national highway. Okay. Generally, the national highways, if you take a small segment, it will be appearing like a straight road, right? But wherever the service roads are there, which are besides them, and the vehicles have to be, which are moving on to the service roads, they have to be get attached to the main road over there. Such cases or such places, we will be having such type of signboards where they have to take a curved path. So, hope this will explain you, or this will give you a clear understanding of what is a translatory motion. Under that, what is a rectilinear motion and what is a curvilinear motion. Let us now go ahead and then see the other type of motion here. Let us say a rotation motion. When I say a rotational motion, I am considering a body over here. Okay. And this is a small particle inside the body. Now, if I just rotate the body over here like this way, now see the type of the motion involved for this particular part. Okay. This will be going, this particular part will be going in the circular path this way. There are two aspects over here. One is the rotational motion, another is circular motion. When we are talking about the circular motion, the part of the body is moving along a circular path with center at point O and having certain radius r. Okay. So, when I say this is the radius of the circular path, that means this part of the body is executing a circular motion. On the whole, if I consider that body is executing rotational motion. That is the difference between the two. It is very clear, evident from this particular example. Let us take one more example where, okay, I will say rotation of the earth on its axis. We know that earth will have two types of motion. One is that rotational motion, another is, yes, you are right, it is the revolution. Revolution of the earth is moving on its orbit in its path around the sun. Okay. But Can that be called as a circular motion? Probably not, because the shape of the orbit is not exactly circle. But when I consider the rotation of the Earth on its axis, you can see the Earth is rotating on its axis. The axis is the imaginary line passing through the North Pole to the South Pole over here. And all the complete Earth is rotating on that particular axis, right? If you consider any particular location on the Earth, say for example India, while the Earth is rotating, India this will be under circular motion. About what? About the same axis about which the Earth is rotating. Okay, let us look at one more example where I'll say there is a motion of a pulley used in drawing water. So if you have come across a pulley over here, something like this, so you can, this is the axle over here, an imaginary line that is the axis, and you draw water from the well using this particular pulley over here. Okay, what is happening over here? See, you pass on the rope over the pulley this way and try to draw the water. Okay, so this way you will be able to have another example of a motion of a pulley used in drawing water. That is an example of rotational motion. Clear? So in this particular example where the pulley is having a rotational motion, whereas the body which is attached to the rope will be having a translatory motion in the upward direction. Clear? So let us move on to the next example of next case of motion, type of motion, oscillatory or vibratory motion. Okay, what do you mean by an oscillatory or vibratory motion? Just have a look at here. I am considering a particle. This particle will be moving from to and fro this way. So it is moving about a particular point, that is what you call fixed point over here, and I say this is the mean position. Okay, the path of this body is moving to and fro about a particular fixed position. Okay, even though I am not explicitly showing it from the mean position, basically this will be the mean position about which the body is executing oscillatory or vibratory motion. Okay, so we do have so many examples in our day-to-day life where we will be able to observe this type of oscillatory or vibratory motion. One example I can tell you, the motion of a sewing machine needle. As the machine is running, the needle will move up and down about a fixed point. That will be coming under this oscillatory or vibratory motion. Same way, I can take, for example, here the motion of a pendulum of a clock. If you observe that, it will be in the oscillatory motion this way. So from one end to the other end, it will oscillate, and this is the path along which it will oscillate. So if you take any pendulum, the pendulum will execute the mean about the oscillatory motion about this particular mean position. Okay, so this can be observed in your clocks or a swing or motion of a pendulum in a clock. This type of motion will be called as oscillatory or vibratory motion. Okay, let us move on to next type of motion, where you call random motion. Means what? When you say random, there is no any particular direction. Can you tell me an example? Let us see first what is a random motion over here. See, if I consider the object over here, just check the motion of this particular object, how it is moving. See, right? Do you have any particular pattern? No, right? So this type of motion of the body, we'll call it as a random motion, right? In so many examples we can consider motion of molecules in a gas. Okay, you might say that we will not be able to see the gas molecules. Then motion of a football kicked in the players in the ground, in the football match. Can you have a particular pattern for the football motion? No, right? It goes the way that it is being kicked, in what direction it is being kicked. Okay. One more example, can you tell me similar example? Yes, honeybee, whatever the way it is going, it is in a random motion. We cannot have any particular path for the motion of the honeybee. Like this, we do encounter so many examples for our motion. Okay, okay. Hi students, while discussing about motion, we encountered so many types of motion, what is rest, and all those things. We generally talk about speed. distance, displacement, velocity, like these many other terms when we talk about motion of a body. When you categorize these particular physical quantities, whatever we have a broad classification, okay, by the name scalars and vectors. Reason is that some of these physical quantities require magnitude as well as direction for their complete description, whereas for some only magnitude is enough. That makes a brief difference between the quantities called scalars and vectors. Let us look at them in brief. When I say scalars and vectors, any physical quantity can be classified under these two categories. Either it could be a scalar or it is a vector. So, when I go with the definition of what is a scalar, it goes this way: the physical quantity whose description is given by its magnitude only. I wanted to describe a particular physical quantity, then only magnitude is enough. That's it. When I say only magnitude is enough, the rest of the other things are not required. Clear? So, let us take some few examples for these things. Length, mass, time, pressure, electric current. So, out of these physical quantities, whatever I wanted to measure, may it be length, may it be mass, time, or whatever it is, I wanted to measure them, I will directly measure them and give only the magnitude. So, I am least bothered about the direction. Okay. So, such quantities we will call them as scalars. For example, if I say mass and length, or if I take only the length itself, I will get one more physical quantity, such a thing where you do not require direction, only magnitude is enough. So, taking the cue from length, I can say area. How do you define area? Area is equal to length into breadth, right? Say, for example, I am calculating the area of a particular thing, particular entity. I wanted to calculate the area. So, area A is equal to, I will write length into breadth. L is length, B is breadth. Breadth means again it is also a length, right? To measure this or this, I just require only the magnitude. If I say this is 5 meter and this is 3 meter, simply I will multiply, I will get this as 15 meter square. So, the number and the unit put together, there is a magnitude, that is enough for me. Okay. Now, give me one more example where you will be able to use area and length and get one more physical quantity which is very much similar to a scalar or which comes under scalars. Got the clue? I am very clearly mentioning that, okay, A is area, you need to use this as well as length. Yes, that is nothing but volume. If I write volume, what is the formula for volume? Right, L into B into H, or else I can straight away write area into H. Apart from area, I have one more quantity here, height. Suppose I will take the same dimensions, I will take H is equal to 2 meter. Then what will be the volume over here? This is already area is 15. So, 15 into 2, that is 30. What will be the unit? Is it meter square? No, right? It is meter cube. Exactly. Right? So, either I measure area or volume. If I go with again taking the mass and volume, I will have one more physical quantity as its density. Density is what? Mass per unit volume. So, mass I know it is a scalar physical quantity and density is mass per unit volume. So, if I wanted to calculate density, I will divide mass with volume. Then I will get the density of any given material. So it also does not require, apart from magnitude, it does not require any other thing. So that can also be considered as a scalar. So all these are some examples of scalar physical quantities. I need not specifically say scalar physical quantities, I can just say it is a scalar, that's it. So because scalar implies a physical quantity whose description is given by only magnitude, that's it. Now when it go with vectors, it is a different one. Physical quantity whose description is given by its magnitude as well as direction, right? So now you got a question like, okay, why it cannot go alone with magnitude? Why you require direction as well? Okay, let us take some examples, then you will be able to understand. Displacement, momentum, force, magnetic conduction, electric field intensity. I can give some more. Acceleration. So some of the terms you might be aware of it earlier, but most of the terms you will learn in your near future. Don't worry about that if you are not knowing these terms. Okay. So these are some of the examples of vectors where they require both magnitude as well as direction for their complete description. Okay. Now you wonder why they should why they should require both magnitude as well as direction. Let me take an example. Okay. Before that, I'll say this one. See, an important note to note, see that all arithmetic operations like addition, subtraction, multiplication and division, they can be used to solve problems where only scalar quantities are involved. So this is an important note for scalars and as well as for vectors, because whatever the operations you are doing, right? So to do that operations, like I have given one example here like volume. In calculating the volume, what did you do? Area into height, right? So area is a scalar quantity, height is also a scalar quantity. I just multiplied them, that's it. That's what the note says. All arithmetic operations like addition, subtraction, multiplication, division. Division, as an example, I can tell that just now what we discussed is about density. In the case of density, we divided mass with volume. Mass is anyhow a scalar physical quantity, volume is also a scalar. So we just divided, right? Same way for addition, subtraction and multiplication, vectors, but for addition of vectors or subtraction of vectors, we need different rules. We cannot just like that do away like what we have done with scalars. This is a very, very important note. Now coming to the point that I am talking about, say, magnitude as well as direction, both are important. For what? For a vector. So why does a physical quantity requires both magnitude as well as direction for its complete description? I'll take a small example. Like see, if I say a body is moving from position A to another position B, this is say along east, then I will say it is going towards north to another position C, that is towards north. Clear? First the body has moved from A to B in the east direction, then it took a left turn, turned towards north and went up to certain distance along B to C. Now the initial position was A, the final position was at C. If I wanted to know the displacement, okay, when I say displacement, basically it is change in position, right? The change in position is from A to C. So I will measure the displacement as this way. I'll draw a straight line like this. Okay. So now its magnitude is different along east, its magnitude is different along north. Finally, if I measure it along A to C, its magnitude is different. Even though the final position is at C, if I wanted to measure the magnitude of displacement along east, I should be able to tell what was the length of A to B, that's it. Similarly, if I wanted to talk about what is its displacement along north, I should be able to tell only the position from B to C, what was the length, only that particular part I need to talk about. So, what is happening here? The magnitude is changing with direction. If magnitude is changing with direction, then we need to specify the magnitude as well as direction both. Only magnitude will not be sufficient. Clear? That is the reason, or that is a main reason why we need to specify direction along with the magnitude. These two are important in the case of vectors, whereas scalars, direction is not required because in any direction you measure, it is of the same magnitude. If I am trying to measure the mass of a body, I do not say the mass of the body is 5 kg in one direction and 10 kg in the other direction, right? So, the mass of the body will be the same whatever the direction you measure. So, there I need not specify the direction, so it is a nature of a scalar. Because the magnitude is changing with direction, I need to specify the direction also along with the magnitude. That is the reason only magnitude alone is not sufficient to describe it completely. Okay. Now, we will move ahead to know how these vectors are represented. We just saw the differences between the basic difference between scalar and vector. Okay. As we are telling that we have a special rules to be followed while doing this operations on vectors, not like scalars. So, for that doing the operations, first we need to know how they are represented, right? How a vector is represented, that is very important. So we will go ahead with representation of vectors. So, basics like say named by using a single alphabet. Certain basic points what we are trying to learn is like how a vector is represented. Named by using a single alphabet or two alphabets and an arrow mark is placed over them. As an example, if I consider say, I will say A, you can see just an alphabet and above it an arrow is there. This indicates that it should be a vector quantity. Okay. If you are seeing the same thing in books, some of the books they will write it as like in a bold letters, they will make it bold. Scalars they will not make it bold, but vectors they will make it bold. That is one style of representing a vector in the books. Okay. So, generally like when we write A, an arrow is placed above it, that represents a vector. Okay. Because when you write you cannot make it like a bold or something like that, right. So, that is the reason we will use this particular type of arrow ahead, above it, just above it, to indicate that it is a vector. So, like a single alphabet, or else the other way is what? Two alphabets. So, when I take that way T, P, Q, that is one example. Okay. Now, why do we have two letters over there and there is an arrow over there P to Q? We will see. Okay. Suppose I mark this way. Magnitude of the vector A denoted by this one. The same A you will write in like pipe symbols on either sides of it, and you will call it as mod of A. Mod of A or modulus of A. Okay. That gives you the magnitude of vector. So, we know that vector has both magnitude as well as direction, or else I say vector requires both magnitude as well as direction for its complete description. If it requires both magnitude as well as direction, we need to talk about the two things. Now, your guess is right, yes, the direction is represented by this arrow, exactly. That means, when I say P to Q, two letters are there, I am very much specifically telling that okay, the direction of this particular vector is from P to Q. When I say direction, from and to should be specified, right? Towards north means from whatever the point I am standing, from that particular point towards north. If I say simply towards east, that means from the point where I am standing over there, or from the point where I am taking as reference, from that particular point towards east. That is what we call about talking about the directions over there. So now I'll represent the magnitude like this, direction this way. Let us see an example. Okay, graphically representation, when you wanted to represent the vector graphically, an arrow. Okay, length of the arrow is proportional to the magnitude of the vector, and the direction of the vector is given by the direction of the arrow. What do you mean by graphical representation? Whatever we have seen here, see, either with a single letter or with two letters over there with an arrow when we generally write. But when I wanted to represent a vector quantity on paper, okay, and I wanted to show it how it is being used or how an operation can be done on it, I'll go with the geometrical representation. Okay, suppose I say a body has traveled 5 kilometers along east, right? I cannot draw a line of length 5 kilometers on paper, right? Yes or no? So what should I do? I should draw a line which is proportional to 5, okay, and then say, yes, this length of this line represents, very specifically telling, it represents what? The magnitude of the vector. That's what we talk about. Whatever you draw it and then show, that's what you call it as graphical representation. Graphical representation of a vector is by an arrow. Okay, the length of the arrow is proportional to the magnitude. Very well I am telling, see, if I wanted to represent 5 kilometers length, I can draw a line whose length is 5 centimeter and then say 1 centimeter represents 1 kilometer. Okay, and then whatever the length is there, that is giving me the magnitude. Direction, whatever the direction I wanted to represent, that direction is represented by the direction of the arrow. The arrow in which direction it is pointing out, that will be showing. Like for example here, I am just writing, I am not specifically taking any direction. One arrow from one point to the other point, I can represent it as A. Or else, by two letters if I wanted to represent, so I will say head and tail, so one is P, another is Q. From tail towards head like this, okay, that gives the direction, P to Q. That is what I represent here, P to Q. The arrow represents from P to Q. That means this is representing, this is the head of the arrow, this is the tail of the arrow. Okay, so this is understanding this tail and head is also important. Clear? So once we know this, the arrow, why is it important? Because this arrow mark indicates the direction. That is what we are talking about here. Okay, direction of the vector is represented by the direction of the arrow. That is the reason this arrow is important. And we do not represent it graphically, we represent it this way, letters, then we clearly mention from P to Q. Okay, let us know little bit more about these vectors. Okay, so two vectors A and B with the same magnitude, different directions. I am representing two vectors. Okay, when I say represent two vectors, I am just taking this way. One is A, another is something like this B. Okay, different directions. When I say different directions, need not be always opposites. Let us say this is B. One vector is going this way and another vector this way. I will say same magnitude. When I say same magnitude means what? Length of this black arrow, length of this orange arrow, both are equal. So magnitude wise it is same. Clear? But what about direction? They are quite opposite. One is going in this direction, the other is coming in the opposite direction. The head of the arrow is pointed in opposite directions for both the vectors A and B. So this gives a clear-cut difference that two vectors A and B with the same magnitude and different directions, they are represented this way. Okay. So in such a case, we will say A is equal to minus B. When I say minus, this minus indicates the opposite direction. Okay. And what does that equal to symbolize as? Equal to is nothing but it is representing the magnitude. When I write simply A is equal to minus B, indicates that the magnitude of A and magnitude of B both are equal, whereas the negative sign before B over there indicates that the direction of B is opposite to the direction of A. Okay. Now, I can also write the other way. I can also write C minus A is equal to plus B. That way also I can write. Okay. If I am taking the direction of A as positive, then the direction of B will be negative. If I take the direction of B as positive, then the direction of A will be negative. So, it is immaterial whether I write A is equal to minus B or minus A is equal to plus B. If it is plus B, I need not specifically write the plus symbol over there, right? So, I just leave it like that. When I say A is equal to minus B, that means this is positive direction and this is negative direction. So, this is as per our conventions what we follow. It is not mandatory that always one is positive and other is negative. So, this is positive and this is negative. We can take that this is also positive and that is also negative. Anyway, we can take. No issues at all. This is clear. Let us look at the other point. See, adding two vectors A and B graphically. So, we know how to represent the vectors graphically, right? That means using pictures or line segments, whatever you call, using arrows. Now, when I am representing a vector A this way, another vector B I am representing this direction. Okay. Now, I wanted to add these two. When I wanted to add these two, what is the rules we should follow? We already discussed that we cannot just like that add like what we do in the scalars, right? Now, one thing to be noted is that as far as addition or subtraction is considered, immaterial whether it is a scalar or a vector. One point we should note it in mind that when I wanted to add two physical quantities, those two must be representing the same physical quantity. It may be a scalar or a vector. Means I wanted to add a distance, I can add it to distance. I cannot add a distance to time. Okay. This is the first basic thing what we need to keep it in mind. Now, when I say distance or time, they are scalars. If I want to add time to another time, I can add to time only. Two times can be added. Okay. Time in the sense durations. It can be in minutes or hours or days or whatever it is. But both are time. Both the physical quantities are time. Two times can be added. Two distances can be added. Two speeds can be added. Okay. And one more thing, that if I wanted to add two scalars like distance, these two distances should be related to the same body. As an example, I can take, see, if I am talking about the addition of one particular physical quantity, okay, like I am telling now, say I have a person Ram and Shyam. I will say this person has done 8 kilometers distance, this has 3 kilometer distance. When I talk about this, I cannot add 8 plus 3 and say total distance is 11 kilometers, because 8 kilometers is the distance of Ram, whereas distance of 3 kilometers is for Shyam, not for Ram. If at all, I will take the other way, that okay, it is same as this is also for Ram. Maybe first trial he has done through 8 kilometers, second trial for say 3 kilometers. Then I can say total distance traveled by Ram is 8 plus 3, 11. So, one thing is, if I wanted to add two scalars, the two scalars must be of the same physical quantity. Second thing is that they should be of the same body, they should be related to the same body or same person. So, this is mandatory irrespective of whether you are talking about the scalar addition or vector addition. Okay. Now, Similarly, when I talk about that here vectors, adding two vectors A and B, if this is displacement, this also should be displacement. Like I discussed just now, this is the displacement of Ram, this is the displacement of Sham. I cannot add those two. Both should be the displacement of Ram only. Maybe first initially he travelled in this direction, Ram. Next again afterwards he travelled in this direction. If that is the case, then I can add these two. Clear? So, whenever you go for addition of two physical quantities or subtraction of two physical quantities, this preliminary points should be always be in the mind. Clear? Now, representing these two graphically, okay, A is in this direction, B is in this direction. I wanted to add these two. What should I do? I cannot just like that add. So, what will I do is like I will bring the tail of one vector near to the head of another vector. Is it clear? So, tail is a starting point, head is a ending point. If A is representing a displacement from this particular position to this particular position, and then B is representing displacement again from this position to this position, I should match these two. That means I should bring this B near to this. I should make an alternate arrangement such that A is in this direction, B is again starting from this particular position. Okay, that means the tail of one vector should coincide with the head of the previous vector. Once I join these two, now this is something like two sides of a triangle. If I wanted to complete the triangle, what will I do? I will draw a line from this here to here, right? But now to add it, we will go just in the reverse way. Got it? Now, when I say from here to here is one side, from here to here is the other side, the third side will be from this point to this point. But in adding these two, what will I do is, I will take it in the reverse way. So, whatever this line is there, the purple color line, this is representing the addition of these two. That means, if I am adding these two vectors A and B, okay, and I am getting the resultant of A plus B this way. So, this will be giving me the addition. So, that is the reason we told like it is not like scalar addition, right? Straight away we cannot add the magnitudes. Now, you just have a guess. If this is say 5 meter, this is say 3 meter, how much should be 5 plus 3? Right, 8. Okay. Now, will you be telling that okay, this length is 8 meters? Definitely not, right? This will be greater than 5, greater than 3, but it will not be equal to 8. It will be less than 8. Clear? So, when I add this geometrically, we will get the vector representation this way, addition of vectors this way. So, this one we will take this way when you have the addition of two vectors this way A and B, and you are getting this as AB, right. So, here we form a rule. What is it? The arrow connecting the starting point of A and the ending point of B gives the sum of the two vectors A and B. This is what we are talking about. Okay, the starting point of A, this is here, this point, and the ending point of B, here, this point. When we add these two and join these two with a straight line, gives the sum of the two vectors A and B, right. So, this is called the resultant vector. Resultant vector, you need to understand this term very carefully. Whatever the effect of A is produced and whatever the effect of B is produced, the effect produced by some of these two vectors is this resultant vector. That means, the combined effect of vectors A and B will be given by a single vector, which you call it as the resultant vector of A and B. Clear? So, that is what we call it as, and this one will represent it like R is equal to A plus B. I will represent R, resultant vector R, and this will be equal to like A and B, A plus B. So, writing the notation, I will write like R is equal to A plus B. but geometrically when I represent it should be this way. This is what you call it as triangle law of vector addition, or you can say triangle law of addition of vectors. Both are the same. So, what does this triangle law of vector addition states? If two vectors are represented in magnitude and direction, A and B, two vectors I am taking, these two vectors are represented in magnitude and direction. So, whenever we are talking about vector, we need to speak about this direction as well as magnitude. So, if two vectors are represented in magnitude and direction by the two adjacent sides of a triangle, adjacent sides. So, one side is here, another side is here. These two are represented by two adjacent sides of a triangle taken in order. Okay. That means, first side I am taking this way, second side it will go this way, third side will be, if I am going in the same order, it will be this way, right. So, then the resultant is represented in magnitude and direction by the third side of the triangle taken in the reverse order. This is very, very important. It should be represented in the reverse order. Now, coming to the resolution of a vector. Now, just if you make a note of it here, see, this is the vector A plus B. I am taking this vector A and this vector B. Okay. I am adding these two vectors, I am getting this. Is it possible that if I am given this vector, can I get these two vectors over there? That is what we talk about, something called resolution of a vector. Okay. Resolve, split. Here the context is resolution means splitting a vector into what? Into its components. So, I am taking this particular vector over here, C. Okay. I am taking O to A. This is representing as A, and OA is represented as A. When I am taking this vector this way, I wanted to resolve this. Now, is this vector in the horizontal direction? No. Is this in the vertical direction? Yes, that is also no. That means this vector is making some angle with respect to the horizontal, right. So, if that is the case, I can split this into two components. When I add those two components, I should be able to get this vector. Okay. Addition of those two components is giving me this resultant. So, if I am splitting this resultant, I should be able to get those two components, and that is what you mean by resolution of a vector. So, I am considering a vector OA in this direction. Okay. Now, I will take along the x-axis over here, something like a y-axis. Okay. When I am taking this along the y-axis this way, now what will I do is, I will check the angle, how much it makes with the horizontal, theta. Theta is the angle what it makes. So, I am taking this particular area, this projection I am taking onto the x-axis. If I take that way, this is the horizontal component. Whatever what is the vector is there, that vector I am taking it a projection on the horizontal direction. So, whatever the projection I am taking it in the horizontal direction, that will be the horizontal component. Now, you can see very clearly this forms a right angle triangle, you can see, right. So, now similarly here also, if I wanted to take a component on the y-axis, this area, that means is showing the projection on the vertical component. So, if I will drop a perpendicular onto the y-axis, I will get a vertical component over there. If I am dropping a perpendicular onto the x-axis, I will get a horizontal component over there. But given the length OA, I want the magnitudes of the horizontal component and magnitude of the vertical component. How do I get that? Just give a thought. It is very clear that this is like a triangle, horizontal, I mean right angle triangle, this part. Even this part is also a right angle triangle. Okay. If this angle is theta, obviously you know that this angle is also equal to theta. Why? Can you give a reason? Yes. This is a horizontal one parallel to the x-axis, and I can say this vector OA acts like a transversal. So, what will happen? these two angles will become exactly, yes, interior alternate angles, and they are equal. So, I can say this angle is also theta. If this is theta, that is theta. Fine. Now, I have a right angle triangle over here with this angle over theta here, or I have one more right angle triangle over here with this angle theta over here. I know what is the length OA. Okay. I want this horizontal part, whereas this angle theta is given. How to relate that? I have given enough clues, right? So, you can use the concept of trigonometry over here and then apply exactly. Cos theta is equal to what? Adjacent side by hypotenuse, we know that, right? So, if I take that cosine theta or cos theta in a right angle triangle OAB, right? Now, adjacent side is OB, this part, whereas hypotenuse is nothing but OA. And what I want is OB. What is given? Theta is given, OA is given. So, I will get very clearly OB is equal to OA cos theta. Simply I can write also, right, OA A cos theta, because the magnitude of OA is nothing but A. Clear? So, I will get this as like OB is equal to A cos theta, that is what I am getting. Clear? So, is the horizontal component, how to take that one, that is clear, na? So, now we will go on that with other component. Horizontal component is A cos theta. Fine. Once we get the horizontal component, let us try to get the component along the x axis. So, vertical component, y axis, vertical component. Now, OAB, this is the vertical direction here. That means, whatever the vertical component is there here, this will be equal to the length AB. Clear now? Now, you already have resolved it. In the horizontal direction, you used what trigonometric ratio? Cos theta, right? So, here I want a relation between AB and OA. Given this angle theta, yes, what should be there? Exactly, yes, it is nothing but sin theta. Now, this part is clear, right? So, when I take opposite side by hypotenuse, this is nothing but AB by OA. This AB will be equal in magnitude with this. These two are parallel lines, they are equal in length. So, whatever AB is representing, that is representing nothing but vertical component. If I take this angle theta, then also I will get this is vertical component, this is this angle is theta, opposite side is vertical component divided by hypotenuse is this OA. So, that way also I will get it as OA is equal to, AB is equal to OA sin theta. I will get this as OB is equal to A sin theta. I am getting the vertical component this way. Is this clear? Now, you see this vertical component of A, where we are taking out A sin theta. This is also along the y axis. So, we also call it as component of A along y axis. Okay. If we take the component along horizontal component, that was called as component along the x axis. Vertical component is also called as component along the y axis, because that is a Cartesian coordinate system what we are taking into account. Okay. Now, we will say an example to how to resolve a given vector into components. Okay. Even though we are talking about the particular kinematics chapter over here, as an example to understand that we will take a resolution of a force that is best understood. Okay. So, with which a block is pulled. So, I am considering a horizontal surface, smooth horizontal surface this way, and on that I am placing a block. Okay. Now, I will apply a force on this particular block in this direction, making some angle. Okay. So, F is equal to 100 Newton. I am applying 100 Newton force on the block, which is making an angle theta is equal to 30 degrees with the horizontal. Okay. Now, I wanted to resolve this particular force into two components. When I am applying force in this direction, what is happening? Actually speaking, in practice, you will have this block little bit pulled in the upward direction also, right? You might be seeing that what you call the trolleys trolley baggage which will carry on. So if you apply little bit force in this direction, automatically the front part of the trolley will little bit rise, right? So same way, so it is rising in the force is being executed in the horizontal, a part of the force is being utilized in the vertical direction also. So I wanted to resolve this force into these two components, horizontal as well as vertical. Okay. So we know that what is the horizontal component here? What did we see earlier? If this is f is equal to 100, this is 30, it will be cos or sin. Which trigonometric ratio will use? It is the adjacent side for this triangle, right? Yes. So it is cos. So we will get it as cos 30. Vertical component, whereas we will get it as sin. So f cos theta and f sin theta. F cos theta is representing the horizontal component, whereas f sin theta will be representing the vertical component. So if I take the horizontal component, it is f cos theta means 100 into cos 30. Now you tell me what is the value of cos 30? Yes, right. It is root 3 by 2. So 100 into root 3 by 2. Clear. So if we simplify it, I will get it as 50 root 3 Newton, which is the unit of force. So this force is as an example we are taking to understand better the resolution of vectors. Now once we get this horizontal component, we also see vertical component. How do we get it? Other component we need to find out now. It is very clear, right? F sin theta. Now what is the value of f sin theta here? It is nothing but f into, that is 100 into sin 30. When I say sin 30, what is the value of sin 30? Cos 30 is root 3 by 2. So what will be the value of sin 30? Yes, it is half. So 100 into half is 50 Newton. Okay. Now when you see clearly, see 50 root 3 is the horizontal component, 50 is the vertical component. If you add these two numerically, will you get 100? Is it equal to 100 or is it greater than 100? Right now, it is greater than 100 because 50 plus 50 is 100, but it is 50, whereas it is 50 root 3. Definitely 50 root 3 will be greater than 50, right? So if we add these two, we are getting something which is greater than 100. So it is not like scalar addition what we go in the vectors. Clear? Whatever the components we resolved into horizontal as well as vertical, if you add those two components by like normal scalar addition, we will not be able to get the vector. So we need to follow the rules of vector addition to add these two vectors, okay, components. So hope this is clear. Now I try to take this particular triangle of vector addition, and one important point I wanted to tell you regarding this. We know that A, B is added, we will get A plus B. Okay. Whatever the component I will take in the horizontal direction for both the B as well as A plus B here, the sum of the horizontal components, sum of the horizontal component of B added to A will be equal to the horizontal component of this resultant. Okay. So little bit confused, right? So we'll check it. See, if I am taking the horizontal component of this, what I am getting? Just this, I am projecting it in the horizontal direction. So this blue part is nothing but the horizontal component. If I am taking this is the angle theta over here, okay, then the angle here is say alpha. What is alpha? Alpha is the angle made by the resultant with respect to the horizontal, and this theta is the angle made by the vector B with respect to the horizontal. Okay, then I can take this is the same angle which this B makes with A. Clear? This is the same angle which B makes with A, because whatever the horizontal component I am getting over here, it is a projection of B onto the horizontal. Okay, when I take that way here, okay, I will get this as, I can write this as, this part is B cos theta. This particular part is B cos theta. So B cos theta plus A, if I consider. Now, if I consider the horizontal component of this, The resultant is this much from here to here. Let me mark this as AO, and this is, say, this point is A, this point is B, okay, this point is C. If I mark this as, what I am getting OC, if I am considering the triangle ABC, this AC is nothing but B cos theta, that is clear, right, so far. If I am considering the triangle OBC, anyhow this is a 90 degrees, that is right angle, okay. So, when I consider the OB, that is, which is representing the resultant, that resultant component of the resultant along this particular direction, if I say, so if I take the triangle, assume the triangle O, B and C, it is right angle at what? C. And if I apply now, what is OC in terms of R? This is alpha. So, I will get OC divided by OB is what? Cos alpha. Okay. So, if I take this way, OC divided by OB is equal to cos alpha. Now, OC will be equal to what? OB cos alpha. This complete from here to here, it is OB cos alpha. The same OB cos alpha will be equal to, what is this OC? OA plus AC. So, this is nothing but OA plus AC. And what is OA? The magnitude of A plus, what is this? B cos theta. So, A plus B cos theta, instead of this OB, now I can write it as R. R cos alpha, this is equivalent to this, both are equal. Okay. So, this way we will be able to represent, that means how the magnitudes are equal, whatever the R cos alpha, the alpha cos alpha into the resultant of this, I am taking the component of resultant along the horizontal, that will be equal to A plus B cos theta. That is what I mean to say. Okay. So, this is how we talk about the vectors and how the resolution of the vectors are done. Hope all these points are clear to you. Let us have a quick recap of whatever we have discussed in this particular session, right. So, first we discussed about what is kinematics, study of motion of particles or bodies without taking into account the forces involved in it, in the motion of the bodies, that is called kinematics. Okay. Next, we talked about the particle or a body is said to be at rest. We are discussing here, we also discussed about rest and motion. So, a particle is said to be at rest if its position relative to the surroundings does not change with respect to time. Okay. Same way, if I am talking about a motion, then a particle is said to be in motion relative to its surroundings if its position relative to the surroundings is changing with respect to time. So, this categorizes the differences between what is rest, what is motion. So, we also know that rest and motion both are relative to each other. That means, if a body is at rest with respect to one body, at the same time the same body can be in motion with respect to another body. Okay. Next, so physical quantity which requires only magnitude for its complete description is called scalar. Same way, a physical quantity which requires both magnitude and direction for its complete description is called a vector. So, here only magnitude, here both magnitude as well as direction should be considered. Triangle law of addition of vectors, if we consider that important law over there, it says that, we also discussed that if two vectors are represented in magnitude and direction by the adjacent side, two adjacent sides of a triangle taken in order, then the third side of the triangle taken in the reverse order will be representing its resultant both in magnitude as well as direction. Okay. So, these are the points what we basically covered, and finally, we also covered what is resolution of a vector. Okay. If any vector is making an angle theta with respect to the horizontal, then whatever the magnitude of that vector is there, that magnitude multiplied with cos theta gives you the horizontal component, and the same thing, the magnitude of the resultant vector multiplied with sin theta, where again I am repeating, theta is the angle made by that particular vector with respect to the horizontal. So, that magnitude of that vector into sin theta will give you the vertical component. Horizontal component is also called as the component along the x-axis, whereas vertical component is also called as the component along y-axis. Okay. Hope all these points are clear to you. Thank you for watching.